Subtract cast 2, which is not listed here. So he already did it. It's not, there's no filter for it. Yeah, that's why we're confused. Just looking at it, like, oh, right, I forgot to do it. Yeah.
Yeah, I don't know what, I guess is she updated the
Okay, so you said you actually wanted to hear about this. So here we go. Another student of mine, Alex Hurley, is working on using optical proxies for density. So density is one of those things you need to know about sediments to figure out how fast the sediment sinks, or how much mass there is per unit of area or optical property. So what we did is use two established methods for estimating density and compared them to an optical method. Now the two established methods are to measure size settling velocity, like I showed that plot with all those data points on it. From that, if you know size, you know settling velocity, you know viscosity, and you know gravity, you can get out what the density is. Okay, so that's one established method. The other established method is to go out and collect water, figure out how much mass is in the water, and then divide it by the volume that you've estimated with a list, or a list paired with a camera like we do. Yeah.
You need to understand what density you're talking about. You're talking about a density of an aggregate that's 95% water.
Right. Right. So what we're going to talk about here is the apparent density, which is the dry weight over the wet volume. Now these aggregates, as Emmanuel said, are mostly water. So most of the volume is in water. So this is units of kilograms per meter cubed here. So normal sediment is like 2650. And what we're getting is values like 10 to 100. Okay, so what that means is that most of it's water. There's not that much dry mass in the actual volume. So that's what we're going to be talking about here, is apparent densities. So I'm just going to go through some plots of Alex's. So this is, sorry, what he's got here is this is the apparent density estimated with the list in the DFC flock camera, or digital flock camera. So what this is CP, the attenuation, divided by the total volume that we measured in suspension with the list in the camera. This is the apparent density estimate assessed with the size settling velocity method. Total disaster. So lots of variability in the CP over volume, no variability in the densities estimated with the digital video camera. The conclusion from this is the digital video camera only images large particles, so we're only getting the lowest density. So this is completely biased, and that's because our camera only resolves 180 micrometers and larger, so only the very biggest particles. So let's forget about that one. Let's go to the next one. Okay, so now we have the apparent density estimated with the conventional methods, which is the measure the SPM by filtration, divide by the total volume, and then we have CP over the total volume here. Bunch of different data sets. What we get is a linear relationship in log-log space. It's a type 2 regression. The slope of the line is not significantly different from 1. It's like 1.05 plus or minus 0.1. So what this means is that these are linearly correlated. So this is a good estimate for this. Yeah.
I'm sorry. Look back to units, the density.
Yeah.
Water is like 1,000.
Yeah. So it's dry mass.
Can you write it down? Just write what the equations are and how you calculate it.
Yeah.
It's not a unit that we're.
In the box, you have a white one. I like
This
white.
one would be Kia.
Yeah, this is excellent.
No, no.
So that's with our particle sizing instrument. So we've got, an aggregate here, and another little guy here, another little guy here. So from these images combined with the list, we estimate what the total particle volume is, and then we filter to get the dry mass. Or you use CP, which is proportional to that dry mass. You can use CP or backscatter. This apparent density is proportional to, you'll love this stuff, really make you ready for lunch. It's proportional to the effective density which equals the density in excess of water. Okay, so the coefficient of proportionality here is rho naught minus rho over rho, where rho naught is the density of the component materials, and this may be flipped. I just don't remember which one it is. So, getting back to your question, water has no dry mass, so the apparent density of water would be 0. So it's just if you have stuff in the water and you divide it by the wet volume. So that's what that is.
So these are measured on discrete samples? Or do you do
These are all bulk. These are all bulk measures. So this is saying, okay, I know the mass concentration in the water from both CP or from a filter.
Can you define rho ALD?
Okay, so rho ALD. And then rho A SPM is SPM over wet volume. And then that rho A DVC that I got came from the expression where WS equals rho S minus rho G D squared over 18 mu. So if you measure this and you measure this and you know these guys, then you can get what this is, which is the effective density, which is proportional to the apparent density. So you just relate it by that proportionality coefficient. This is independent of this. Okay, so ideally you want to use this estimate and get it to agree with this estimate because they're independent measurements. These guys aren't independent measurements because they're both using wet volume. Okay, so really all we were looking at is whether CP is proportional to SPM. So that's the dirty laundry part of it. So this, as we saw, didn't work. Okay, and that's because we were only measuring the biggest particles.
But what happens if you use, so one of them you have the camera and the piece to do the wet volume. But ideally this method you want to use with the list alone if you could. I know you looked at it already.
Yeah, so we'll get to that. Okay, so this is linearly proportional to this. So it's just really telling you that you can use CP as a proxy for mass in a whole bunch of different environments. Now, you'll see that the data sets plot out differently here. This is compositional. So we've done nothing to correct for the composition with backscatter ratio, but that's what we infer this to be, is that you're in either more inorganic or organic environments. Okay, so now we did the same thing as Emmanuel suggested with the list, okay? So because lots of people have lists, not very many people have digital flock cameras, you would want to be able to do the same thing, just CP list over the volume list. What we get is that there is still a significant correlation here, and we could get rid of a lot of this variability by using the backscatter ratio, which we haven't done. But it's no longer a linear relationship, and that's primarily because of these OASIS 2011 data points, which are kind of jigged off over here, and it's pulling the whole slope of the line down. So the slope of this line is more like 0.75 rather than 1. So still proportional. There's a good correlation there. You could use this as a proxy for this density, but it's no longer linear. All right? So what this means is that you would end up with the list, you would end up overestimating your lower densities. Okay, so this is how we showed that the camera had a bias problem. Here's the Dvc method. So what this is we're using this equation to estimate what effective density is and then using this proportionality to convert it. And those are the dots along here. And then the circles are using the LD method, and this is for one data set. And these are plotted versus the median particle diameter. Now, a thing that's known about natural marine particles that are aggregated is that the density goes down as the size gets bigger. The LD method is showing that. The DVC method is, and it's always pegged at these low values. So it's just biased to seeing the big particles. So to solve this, what we need to do is have a camera that looks at smaller particles, and we have one under development. But right now, that's a problem. Okay, that's a bad old figure. This was, yeah, it's a bad old figure. So I hope the new figure's in here somewhere. Okay, I'm going to go get the other. Figures. Hey, what happened? Oh, I see. Okay, so that's the figure that we were looking at. I hope that the corrected ones are coming up. Okay, so you remember that terrible figure we were looking at? There were some fouling problems that hadn't been corrected for in looking at total volume from the camera and the list versus volume just from the list. Okay, so that's what we have plotted here. Here's the total volume from the camera and the list, and here's the volume just from the list. What we see is a nice linear relationship, which is great. It means that you don't have to go out there and measure all of the big particles, because you know that in general the volume that the list sees is proportional to the total volume. So you just have a nice marching up the size spectrum of the stuff, and Colin was kind of referring to that before. There's some bogus points down here which are generally from when particles get too large. But also what you see here is that this nice linear relationship, which has a slope of about 2, so that means the list is picking up about half the total area, you start falling off at larger sizes. And the reason should be obvious. If you move out of the size range of the list, so you get above 250 micrometers for the type B or above 500 micrometers for the type C, the list no longer sees the particles in suspension. It starts doing crazy stuff. It starts seeing secondary peaks. So what happens is you start losing that proportionality at really large sizes. That's what ends up explaining. There's what it looked like before we cleaned up the fouling problems. Oh yeah. So what this one shows is if your solder diameter is less than 80 micrometers, you fall on this really tight linear relationship here. If your solder diameters are larger than 80 micrometers, you start falling off of that line, so the list stops seeing all of the volume that's there, or it stops being proportional, and you get this up here where it bends off. All right, so.
But how do you know where you are if you're just taking this measurement? You just don't know.
That's a significant problem, because we can diagnose it with the merged size distributions, but if you have the merged size distributions, why would you just use the list? So that is a problem. We don't have a solution at this point. It's like, well, you just have to be aware that your list, there could be bigger stuff out there, which you should be aware of using a list now anyways. I mean, there's enough stuff in the literature now saying big particles cause problems that you should be aware of it. But most of the time in that plot, most of the time you're at least linearly correlated with the area. So OASIS 2011 had particularly big particles in it. Big.
Where's Oasis?
Sorry, that's Martha's Vineyard Coastal Observatory. So that was a data set where we had a lot of big particles. This doesn't show up because I think Alec is doing it for publication. But what this shows now is time series of this rho A term, this apparent density, as a function of year day in 2007 at this site, Martha's Vineyard Coastal Observatory. It's a bottom boundary layer, 12 meters of water. It's a wave-forced environment. What we have here is the time series of the apparent density. Up here we have time series of the shear velocity, which is a measure of the stress on the bottom. And we also have time series of the attenuation in the bottom boundary layer. The gray is that shear velocity, and the black is the attenuation. I guess I could use this pointer guy here. This is a neat neat little run here. So this is a period of about a month. So what you see is that there's a wave of this environment. The shear velocity goes up because of waves. So there's a wave event. Not much happens, and then you're getting into the stormier and stormier time of the year. This is beginning of September, and we're going through the month. And then you get a really big event. And what you see here is that the shear velocity peaks, but the CP lags that. So what's going on here in this environment, there's a limited supply of sediment, resuspendable sediment on the bottom. So the shear velocity cranks up and you make a really big fat bottom boundary layer, and you mix that sediment that was available through that whole big thick fat bottom boundary layer, so the CP is not that high. As soon as the stress starts to go down, the boundary layer thins, the particles fall into that thinning boundary layer, but the stress is still high enough on the bottom to keep that stuff from depositing. So what you see is an increase in the concentration, or in the CP there, and then you see the same thing in this later event. Well, what happens with the density? So here we're going along with the density, and what low density means is big particles. Okay, you make low density particles by making them really big. So what we see here is that after these events, so there's an event, you see a drop in the density. And then the density goes up, and then here we see the densities are high initially, and then they go down right at this period when the CPs are high. So what we're seeing is evidence of flocculation dynamics here. So you stir up some sediment, and then you turn down the turbulence, and that allows flocks to form, which have low density. And that's what we're seeing here. So by looking at this time series of density, you get a different view of what's going on with the particles. Why does it go up when it's calm? That's because you lose the big low density flocks from suspension, and you're just left with little denser bits, the small denser guys. This is CP to volume list. And so this is our total merged volume estimate, and this is the one just with the list, and looks pretty good. Okay, so yeah, when you go low, it doesn't go as low as it should, but it's still going low at the same times, and it's going high at the same times. So we think this. So at the end, Colin, we can't diagnose with just the list if you're running into problems, but it doesn't look like the problem's that acute. Now, if we did the same thing with 2011, we may see more of a problem, but 2011 we had really bad fouling problems, so we can't really do as nice a time series as this. But with Chris Sherwood, we have a really good time series that we'll someday be able to put out there too. Okay, so that's the other thing I was going to talk about, but I didn't prepare. Okay, that's what I got.